fill out the questionnaires which are in front of you. And not many have been completed yet, so that would be great. The other thing is that a reminder that the talks and the associated videos will be online in about 2 weeks' time from now at this web address. If you're a speaker and didn't upload your talk to the laptop, please send your or upload your talks through this address as well. Okay, thanks so much. Mike Titterington would like to say a few words as
well. My name is Mike Titterington, and I'm one of the organisers of the programme of which this workshop is part. And I'd really like to say thank you on behalf of my co-organisers and the Institute to David especially, and Sylvia and collaborators for all the effort they've put into organising this workshop.
Thailand as well.
This was completely their initiative, which we were happy to support and have the reflective glory as part of the programme. But they did all the work. They applied for and gained Pascal funding. They managed to persuade wonderful people to come and talk, and other wonderful people to come and listen. So I really think they deserve a very strong thank you.
Right, over to the final hurdle. I didn't mean that. I meant the final straight, actually. I'm not. Okay, so Sophia is going to present the following talk: high frequency variability and microstructure bias.
Okay, well, thank you very much. And that's not quite correct, because for the first time in my life I'm actually doing a double act, so I'll be speaking for the first 20 minutes. And then when you're just about to fall asleep, Adam is going to rescue you and go through the end results. So this is joint work with Greg Pavliotis, who's also at Imperial College. So I'm going to be talking about observations of SDs which have been immersed in high-frequency noise structure. And the outline of the talk is going to introduce the problem. I'm going to talk a little bit about previous solutions to these problems, which are based on some variant of subsampling. I'm then going to talk about multi-scale understanding of what actually makes the process take the sort of realized structure that we see. I'm then going to introduce two concepts which will help us formulate new estimators of the integrated volatility of the SDs that we're observing, namely the multi-scale ratio and the multi-scale likelihood. We're then going to have a little look at what the results appear to be doing for the Heston model. We're then going to extend the whole method to having correlated and not just white noise high-frequency structure. And this will require some adjusting of the concept of the multi-scale ratio. And finally, we're going to make some conclusions and discuss some further extensions which lie ahead. So to give you some sort of intuitive understanding of the problem we're dealing with, Adam has very kindly simulated a realization of the typical thing we might see. So we're interested in estimating the integrated volatility of the red curve here. That's the underlying process which is of interest to us. Unfortunately, we do not observe the red curve, but we actually observe the green curve, which is the underlying process of interest which has been immersed in high-frequency noise. And if you're interested in the underlying volatility, what's going to happen is you're going to get lots of contributions which are due to variability from the noise, and you're going to get hopelessly biased estimators. So just to give you a little bit more of background of where these problems come from. So we're thinking again of modeling in terms of continuous time stochastic processes, and we're thinking of immersion of these observations in some high-frequency nuisance structure. And in fact, it transpires that this is found in many, many different fields. So a lot of observations or sort of interest is focused on financial time series. I'm here referencing the work of Zhang, Aitzahali, and Miklun, for example. They're also prevalent in atmosphere and ocean science, where the problem is even more difficult, because here we just have a problem that the nuisance structure is biasing our results. While some work I've been doing in terms of oceanographic data, you have to understand the high-frequency structure to see how the problem actually evolves. but it turns out that high sort of numerical models for the entire world can't really incorporate all of the high frequency structure, and so you need to parameterize the effects of the high frequency behavior on the sort of main features of the data, and they're also found in molecular dynamics. So a sort of common model for these problems is to think about a sampled, sort of unobserved process, which is the process of interest that you want to make inference about the properties of, which we'll just call X. And unfortunately, you can't observe X directly. So Omeros discussed these problems as well in the previous talk. But it's been immersed in some nuisance structure, which we'll, just to start off with, model as white noise. So in a way, you might say, this is a very simple sort of thing to be thinking of. We just have structure of interest in white noise. But the problem, or what makes this difficult, is that we're actually thinking about a continuous time process. And usually when you have a continuous time process, you think, oh, get more and more frequent observations, and you figure out a lot more about the process. But what actually happens is, because of the noise having the same properties, as you start sampling more frequently, it completely drowns out the other structure. So again, xt is the process we're interested in, and we'll model it in terms of a stochastic differential equation. Okay, so there are many different things we could wish to estimate in this scenario. We're going to focus our interest on the estimating the integrated volatility of x. And what you do, you know, if you had sort of just wanted to make a really simple estimator of the integrated volatility, is you just look at the quadratic variation, and unfortunately, because you do not observe x, you only observe y, you'd start to take differences of y and just sum up the square differences. So if there was no noise, this would be a perfectly okay estimator. What happens when you add noise is that a lot of counterintuitive things start occurring. So Zhang et al., for instance, showed that just starting to subsample the data, i.e. throwing away lots of these observations, and thus increasing the sort of sampling period, would actually improve your estimator. So this is, I mean, to a statistician, you know, the first reaction when you see this result is, you know, go and get lost. You know, you must be kidding me, because of course throwing away data is counter to our nature. But the problem is, if you start having more and more finely spaced data, the noise completely dominates in that expression. So in many of these problems, generally it's preferable to subsample rather than not to subsample. So of course, once you see that it's good to subsample, you start thinking, what about you start subsampling and then you start sort of averaging across all possible subsamplings or something? Well, you can actually improve on the basic subsampling method quite substantially by first finding a good subsampling rate, and then from the subsampled estimator, figuring out what the bias is, and then do a sort of delicate process of correcting for the bias. So that's sort of the background in what, I mean, other people have been working on these problems as well. So for instance, Jianqing Fan has developed an estimator based on using wavelet functions. But we started looking at this problem, and we thought, okay, if we're thinking about structure that enters here because of the noise, it's not very transparent to start looking at the actual formulation in the time domain to figure out what's going wrong in the estimation. In fact, the reason why this is behaving really nastily is a lot more apparent in the frequency domain. So our first thought was just, okay, forget about the time domain, let's go straight to the frequency domain. Of course, we want to start looking at lots of differences of processes, so we'll start introducing some new notation where for an arbitrary process z, the first difference we'll just call u of z. So we say, okay, we have this object here, let's first figure out what does this bias come from if we go frequency domain. And of course, someone should just stop me here and say, how do you know you can go frequency domain? I mean, the Fourier transform of this process need not be a well-defined object. Well, we're going to discuss a little bit later what assumptions we need to make. So to start off with, well, not a little bit later, actually now, xt is an eta process. We're going to assume that once we sample it and difference it, it's a harmonizable process. Well, what's a harmonizable process? That's simply a stochastic process where it's okay to calculate Fourier transforms. We also will place various technical assumptions on the decay of this object here, which is the Lerve spectrum of the Ito process once it's been sampled and differenced. You might now ask, what's the Lerve spectrum? I've got no idea about that. Well, basically, if you calculate the Fourier transform of the process once it's been sampled and differenced, and you then look at the correlation of the Fourier transform at two different frequencies, that gives you the Lerve spectrum. So the technical assumptions here are partially sort of assumptions regarding the correlation between different frequencies which are not equivalent. Then it's fairly trivial to get an understanding of what the microstructure noise is doing to the quadratic variation. So if we have a look at just of the expectation of the biased estimator of the quadratic variation, where we now assume we're calculating it over a time interval length t, we find that it's actually a combination of the Lerve spectrum, which is just here evaluated at the same frequency, so it's just the variance. So this is sort of expressing a Percival-Rayleigh relationship between the variance of the difference processes and the Fourier, the sort of variance of the Fourier transform. But then on top of that, unfortunately, you get the effect of the noise. And I mean, from here, it's really apparent what's going wrong. So at the low frequencies, you'd expect this to have sort of reasonable contributions. But of course, because you've differenced, once you have the white noise, this gets bigger and bigger and bigger. And at high frequencies, the effects are quite remarkable. So of course, once you change delta t, the sampling, these effects are going to be exasperated. And of course, there are some error terms in the expression, and I'm not going to go into them here. Okay, so just going back to that, we see the problem is because of the noise effect, and it gets worse at higher frequencies because of the sine function increasing. So we can just sit back a little bit more and think, okay, we can rewrite this sort of a biased estimator in terms of just the estimated Lerve spectrum of the observed process just directly as a sum. This is a simple Percival-Rayleigh relationship. Then the problem arises, as we just saw in the previous formula, because the expectation of this object is not the Lerve spectrum of x because of the noise. So sort of trivial. Go back here. Basically, it ends up being a sum of the spectrum of y, which is just that plus that, because we assume uncorrelatedness. The obvious problem that arises is that the expectation of the spectrum or the Lerve spectrum along the diagonal of y is not the Lerve spectrum of x. Okay, so I mean, what's the obvious thing to do? Well, basically what's happening at the higher frequencies, we're overestimating the Lerve spectrum of x. So the simplest thing to do is just to correct the usage of the Lerve spectrum of y by just multiplying it by a factor. So we now produce a new estimator of the Lerve spectrum of x by just introducing this factor Lk and multiplying that to the Lerve spectrum of y. Bravo, we have a new estimator. Okay, well, the problem is that's all very well and good. How are we going to pick L? And L, this object that we need to multiply the Lerve spectrum of y by, will refer to as the multiscale ratio, and y will become obvious in a little while. So having decided that we need to multiply the observed spectrum of y by a factor, we now need to decide how do we determine what that factor is. Well, trivial algebra is just going to show you that the correct form of that factor is just whatever the Lerve spectrum of x is divided by the Lerve spectrum of x plus these nasty contributions we get from the noise process, which get worse as we're looking at high frequencies. So the obvious thing to do is you say I define a new estimator by looking at, estimating the integrated volatility of x by, instead of just summing over the estimator of the sort of spectrum of y, or the Lerve spectrum of y along the diagonal, we'll introduce a new family of estimators which which are going to be defined simply from the previous page by multiplying the old estimator by a factor which lies between 0 and 1. And if we then choose this unrealizable value of factor to multiply the spectrum of y by, we'll end up with an unbiased estimator with some error terms. Well, basically these are not so important. They depend on the correlation of the frequency Fourier transform of y with itself at different frequencies, and these can be bounded if you make some reasonable assumptions. So if you just were to take this factor, multiply the observed spectrum, you'd end up with an estimator which was unbiased. Bravo, okay. But the problem is it's unrealizable. It's unrealizable because, of course, if we knew what the Laue spectrum of X was, we wouldn't really need to be doing anything at all anyway, because we could just sum that up over all frequencies and we'd get an unbiased estimator anyway, right? So this would be a procedure that would give you a good estimator, but we can't implement it. Okay. So let's think a little bit more about what the sort of elements of this procedure is. So a sort of measure of the total energy of the process of X, and people who are familiar with stationary time series will realize that usually if you integrate over all frequencies, you end up with a variance. So here, when we use the Laue spectrum, the frequency domain contributions are expressed in the Laue spectrum instead of the normal spectrum, but still, you'd get a measure of the total energy if you just integrated out the Laue spectrum along the diagonal. If the process, on the other hand, is non-stationary, then you can write the average variance in terms of integrating out the Laue spectrum, and again, for various reasons, there are some small lower order contributions. So in a way, we see we don't have this object here, which is the unknown spectral contributions from the Laue spectrum, but we know that if we average them, we get the average energy contribution across all frequencies. So to sort of show you where I'm heading, obviously the object I'm trying to approximate is this LK. I don't know what I should put in for these, because if I knew them, I wouldn't have a problem. So I'm now starting to argue that a typical measure of the values these would take is given by the average frequency contribution across all frequencies, and that we could think of as a variance. So this is not a rigorous argument. The way we really want to think about that is, what does the frequency contributions of the process of interest look like compared to the frequency contributions of the noise process? And basically, the frequency contributions of the noise process become large as you go to higher frequency because of the sine terms. But it turns out that for many processes, the typical frequency contributions from the process of interest bumble along at the same level. That, again, I say, it's not a rigorous argument, but we're making the assumption that we can replace LK by sort of average ratio across frequencies, which is just going to be a constant associated with the X process, and a constant again, plus the term that came from the sine. So this is a slight leap of faith, but it allows you to quantify how biased a contribution you're getting from each frequency from the noise process. This is probably when Adam kicks me off the stage. So having decided that we're going to replace the total spectrum, which varies across all frequency, with a typical energy level, we now need to assign a value to that typical energy level, and we need to assign a value to the sigma epsilon squared, which is associated with the noise. So of course, the obvious way to go here is to say, well, I'm going to pretend a while just like the typical energy value was the spectrum and the variance of the process across the different frequencies. So I'm going to think about looking at a sort of likelihood approach to picking these sigmas, both for epsilon and x. Okay, so now you'll all stop me and say, the process was harmonizable. This is not a likelihood for the Fourier domain description of the signal. So we sort of see these are the typical elements you'd see in a stationary likelihood for a time series. You've got the estimated spectrum of the Y process, you got something in lieu of the typical variance, and again you have the log term, which is part of the typical likelihood you'd get for a stationary model. Well, basically, if you combine this with the assumptions we made for the correlation structure across the different frequencies, you can show the values you pick for the sigmas, if the process had been constant across frequencies, would indeed give you good estimates for sigma x and sigma epsilon. But strictly speaking, this is not a log likelihood. It's simply a function that we maximize to pick a reasonable value for sigma x and sigma epsilon. So having done that, we can now calculate an estimator for the bias-corrected version of the quadratic variation. Okay. So I'll slightly sail through this. Adam will have some time. We calculate estimators of the typical energy for x and the noise variance for epsilon by doing maximum likelihood, even though it's not a likelihood function. And you can show various properties of the estimated multi-scale ratio you get out of this procedure. I'm not quite going to go through them. It's on the preprint on our web. Furthermore, you can show that once you choose this bias-corrected version of calculating the estimator of the integrated volatility, then, and this is exactly what you would anticipate, you find that the expectation of this estimator firstly gives you out exactly what you want to have, namely the contributions that comes to the variability from each frequency. Secondly, you get a term here which exactly is quantifying how much you're giving up by the fact that you don't have a constant contribution in x across frequencies. After that, you get a contribution to do with the fact that the noise variance you estimated is not exactly the true noise variance because you again lied with this likelihood. And you can also quantify the total variance. So as I said, you get a measure of the deviation of the estimator, which is due to the fact that you don't have a constant contribution across all frequencies from the process of interest. And you can also write down exactly the form of the variance. And again, you can show that the variance you get out by using this estimator rather than the normal quadratic variation is actually strictly less. It's strictly less unless we always multiply the spectrum by 1. And now Adam will show you some motivating examples.
Right, so for the remainder of this presentation, I will show to you how and why our multiscale estimator works in measuring integrated volatility. And we do this through a simulation study. So the model of choice is the Heston model. And this is as done by the work by Zhang and Neitzer-Halia in measuring integrated volatility in the time domain, their improved methods. So we mirror what they do. And yeah, so here is the Heston model. The X process driven by a stochastic differential equation, and the volatility process itself also driven by an according SDE. And for the noise process, we initially, the market microstructure noise is white, and we deliberately set this to be small, again mirroring the work of Zhang and Neitzer-Halia. So here we see how this actually all looks like in the frequency domain. So these are the Fourier representations of the process of interest. On the left is the periodogram of the UX, the X difference process, and on the right of the noise process, U epsilon. And this is done over a sampled length of data of tick by tick or second by second data of length 23,400, which simply corresponds to one trading day on the New York Stock Exchange, for example. So the first thing to note, I apologize for the fact that you can't see this very well, are the scales of the two graphs. So on the left it's magnitude 10 to the minus 8, and on the right 10 to the minus 6, which means at the higher frequency end, almost all of the energy is coming from the noise process. And this is, we can see this very abruptly in this representation. However, at the lower frequencies, of course, then we see that actually most of the energy comes from the X process, and at zero, none at all, of course, because of the sign function from the white noise. And in fact, as a result, the periodogram of the Y process, the process that we observe, to the eye looks exactly like the graph on the right, which is why it's not included again. And it's from that periodogram that we make our estimates of sigma squared x, the line on the left, and sigma squared epsilon on the right. And as you can see, from our multi-scale likelihood that we've developed estimates that are seemingly not only the right magnitude but also the right shape for the kind of data we're observing here. So we apply our estimates into what Sophia introduced, which is the multi-scale ratio, which our estimated one is the white line here, which is superimposed on top of the actual optimal ratio, which we can't observe. And what we do is we apply this frequency by frequency. We multiply this with the periodogram of our observed process. And of course, we're wanting to remove all this energy from the high frequency. And this is what we'll do. We're near zero here. We're going to drastically reduce it, but retain all the energy at the low frequency end. And in theory and in practice, we should recover bias-corrected estimators that look like the initial graph we had of the UX process. And on the left, this is the one using our optimal multi-scale ratio, and on the right, actually using our estimated one. And what we've managed to do is correctly remove the correct magnitude of noise from the high frequency end, and obviously retained all the energy at the lower frequency, and we've got something that, at least visually at this stage, looks how it should, essentially. And we'll see later through some Monte Carlo simulations and so on that this indeed holds. But before we do that, I'm going to move on to an extension looking at correlated errors rather than just moving away from the assumption of white noise. As most of you know, we can represent a stationary process using the world decomposition, this infinite sum here, with some regularity conditions. However, in practice, we wouldn't use an infinite sum. We would try to approximate by a finite number of elements in this sum, namely Q. So, given this, we can have an explicit spectral model for our noise term, governed by this stationary process, and we can literally put this straight into the method that we use and develop an augmented multi-scale likelihood and augmented multi-scale ratio with this more sophisticated model that models correlation in the noise terms. And if we don't know Q, then we can apply various ways of finding it, but that's not the subject of this talk. Once we have Q, then we have Q parameters in the MA process that we need to estimate together with the actual magnitude of our noise and the actual energy of the X process. So we have Q plus 2 parameters we have to estimate in our new augmented multi-scale ratio. And we can do this in exactly the same way as before, but in a more sophisticated way. And now we have a new estimator that takes this form where quite simply we've replaced LK hat with LK hat A for augmented, where we've simply performed multi-scale likelihood over more parameters to look at a more complicated noise process. So to look at see how this actually looks, we'll investigate the simple case of an MA1 process, which the process itself, not the difference process, has this simple spectral form. Of course, if we set θ1 to be 0, we just recover the flat white noise spectrum. But obviously what's really interesting is to vary θ1. And the idea is that if we make this positive or negative, this very much changes where the energy of the, in what frequencies do we see the energy of the noise process appearing. And it very much depends on what θ1 is. And the idea is that our new estimator will adapt to this in theory, because it will try and estimate θ1 hat by looking at the observable data. We don't change our X process. We continue to use the Heston model exactly the same as before. So we've just changed the noise here to a more sophisticated model. And this is what happens. So this is, again, the Fourier representations of the unobservable process and the noise process. Again, with the same scales, 10 to the minus 8 on the left, 10 to the minus 6 on the right. The X process, nothing's changed. As we'd expect, we haven't changed anything. But what has drastically changed is the shape of the noise process. And what we're seeing now is, because here I've set θ1 as 0.5, so we're getting a reasonably strong positive correlation in our noise data, tick by tick. And the effect of this is that we have much higher energy in the mid-frequency range. We still have none at lower frequencies, and we have less at higher frequencies. And now the contamination, in effect, is in the mid-range frequencies. And again, from the periodogram of UI, we estimate these, and we've, again, seemingly done this well. So here we've estimated not only the magnitude of the noise, but also θ1, which tells us the shape of the noise process on top of the sine functions. And this is exactly what we put, again, into our multiscale ratio, which is the graph on the left, our multiscale ratio. And you can see how it's adapted to the new noise that we have. So we're going to be significantly reducing the energy in the mid-range frequencies, which is what we want. Still reducing a lot from the high frequencies and retaining all of the energy in the lower frequencies. And on the right, we can see what happens when we multiply this ratio by the observable process, the periodogram, and we, again, retain a good approximation, a bias-corrected estimator of the unobservable process, which we didn't know before. So in theory, again, and in practice, this should recover a good approximation of the integrated volatility. We simply sum this graph across. So we performed some Monte Carlo simulations, again, over one trading day, except we did 7,500 such paths, which in theory is 20 years of financial data. So quite an exhaustive simulation study. And I'll draw attention to the fact that we've done this over varying types of MA1 correlated noise, ranging from -1 to 1. And here we've included the results of 5 different estimators. On the left is the most naive approach of just taking the quadratic variation of the Y process, which, as we know, motivates this study as this produces disastrous results, even though, I reiterate, the noise we've modeled to be small here. On the right is the unobservable quadratic variation of the X process. This, in theory, is our benchmark figure. This is the closer we can get to this, the better, basically. And in the middle, we have the 3 developed estimators that have been mentioned in this talk. The first one is the time domain estimator by Zhang, Maikland, and Sahalia. Then we have our estimator based on a white noise process, and then the augmented one based on a moving average noise process. And first, if I just draw attention to the results we get when θ1 is 0, which is in effect white noise. Of course, we do terribly when we just take the quadratic variation of the observable process. We have much higher error than root mean square error. This is then with the observable process. And in fact, all the estimators here do very well. I'd like to note, of course, that our estimator does here marginally better than the time domain estimator, which is a result we're quite happy with. And in fact, an even more striking result is the fact that we don't even do that much worse when we're looking for correlated noise, even when it doesn't exist. So here we're pointlessly, in effect, trying to find θ1 because it's 0. And we actually find it to be 0 and have minimal loss in performance. Now, what's really interesting is what happens as we move away from white noise and move to correlated noise. First of all, our augmented estimator adjusts to this, so we continue to do well across the range of θ1 here. We actually do better marginally when θ1 is negative, and that's simply due to the shape of the spectrum of the noise process. So the scale separation is much easier here because here we're having huge contributions from the high frequency end. Whereas here we're getting most of our contributions from the mid-range frequencies. The scale separation isn't as obvious. And even though we've still done this well, we haven't done it quite as well. Both the estimators obviously do worse. Both of the estimators based on white noise do worse as we move away from white noise, as we'd intuitively expect. Interestingly, the time domain estimator, we do worse symmetrically as we move away from theta 1 equals 0. Whereas actually with our Gaussian, in the frequency domain, we actually do better for negatively correlated noise. And again, this is for the same reason as before. This is because here we're having the energy from the high frequencies, which we're removing, but ultimately removing too much from the mid frequencies because of the shape. Whereas here we're failing to remove all the energy from the mid-range frequencies because we're expecting it to be at the high frequency end. So we've missed out on the noise contamination here and done rather poorly. However, of course, I reiterate that our augmented estimator does pick this up and does well. So to conclude, we've developed a method for estimating integrated volatility based on Fourier domain representations of all our processes. And what we do is we model the market microstructure noise parametrically, but I reiterate we do not do that with the underlying X process. We're simply trying to model the level of the noise and then debias this locally at each particular frequency. Time domain methods try and do this globally with a global bias reduction, perhaps by trying to estimate this and remove this, but we actually do this frequency by frequency and believe that we get better precision and power by doing this. And we demonstrated this using Monte Carlo simulations. We also extended to look at the case of stationary processes, namely MA1 noise processes, and we managed to improve our bias correction at each frequency for this noise structure. So future avenues of investigation, well, obviously involving rigorous model choice procedures, trying to perhaps estimate the Q in the MAQ process to see what kind of noise processes we typically get, and the application of Bayesian estimation methods to incorporate the multiscale ratio by hierarchical modeling. And I'll just conclude by saying that we believe multiscale modeling shows great promise for designing inference methods in such processes, just by this increase in precision and power from doing things scale by scale, frequency by frequency. And then just included some references. There's our first paper at the bottom. If you're interested, please look it up on the web. And also, if you're more interested in time domain estimation of integrated volatility, then please look at the work of Zhang, Michael, and Aitzahalia. They have several papers, not just this one, as well. But we encourage you to keep an open mind and look at our work as well. And that's it. Thank you very much.
A couple of questions.
Is there a way of testing this in real world?
Work in progress. Well, testing it by looking at financial data in the real world and trying to see if our measure of integrated volatility is sensible and corresponds with industry practice and perhaps improves. Of course, the problem with using real data is you don't know the real answer.
Was there any aspect of
If you move to tick by tick data, how do you plan to estimate the spectrum?
Loom periodogram, Scarville, 1979?
But is that okay? Because the frequency are more or less related, so it does not enjoy the same properties as the standard variogram because
No.
That's not done very correctly.
So you have to do the extension slightly more carefully, but you would base it on the variable. You have to be careful with the contributions of the total covariance between frequencies, and it's possible that you need to subsample the frequencies. You'd have to study the actual failure kernel for that particular sampling.
I had a question about perhaps maybe Omiros can respond. But if you were to just do sampling of the posterior distribution of your x's given your y's, and just use your best guess sampling procedure, would that be a good way to proceed? Or?
So then you'd also be trying to estimate sigma epsilon. So
Yeah.
it should give sigma. But you have to formulate the likelihood again. I'm not sure how
So
it would pan out.
Omiros is not doing that. Why can't we just simulate just do the posterior sampling of the posterior in this case?
And reconstruct the volatility on the basis of
Yeah.
that, you mean? At least,
Seems to me we're putting in more things here, like our understanding
course
of
that-
frequency properties. And if you don't put that in there, how can you possibly get the same result?
I don't know.
I mean,
he
when
has
you
an
move away
opinion.
from the IID error, then unless it's Markov, it's not going to be that. I mean, if you work with this main model, obviously you lose the Markov structure. But if you have some kind of discolored noise, like OU process, maybe it's interesting.
Yeah, let's thank both speakers.